Thank you so much. Thank you for organizing this wonderful event, and thanks for the invitation. It's a pleasure to be a part of it. So let me start sharing my screen. So I will be talking about life beyond Earth, what makes a planet habitable. So I'm Dimitra. I'm from the Center for Space Science at New York University in Abu Dhabi. So in case you were wondering how come New York University is in Abu Dhabi, 10 years ago NYU became a global campus. And in addition to a campus in New York, it now has a full campus in Abu Dhabi and Shanghai. So three degree granting campuses, one university. And the interesting thing is that the three countries where the campuses are located, all three have missions going to Mars right now. So UAE has the HOPE mission, US has the Mars 2020 Perseverance, and China Tianwen-1 mission. They're all on the way to Mars, and they will be inserted to the Martian orbit in about a month from now in February. I will come back to Mars later on. So let us start with planets. Here is a slide showing our solar system. Some of you might be upset that Pluto is not here. There are two types of planets that we see in our solar system. One is called terrestrial planets or rocky planets, such as Mercury, Venus, Earth, and Mars, where it has a surface, you can go and stand there. And the others are gas giants. And as the name suggests, these are giant planets full of gas, mostly made of hydrogen. We also live in a galaxy. This is the Milky Way Galaxy. That is our location right over there. There are estimated 100 billion stars. This is a conservative estimate. And based on the human population right now, just to give you an idea, it is around 14 stars per human being on the planet. The nearest star is about 4 light years away from us, which means that it takes light 4 years for that star, for light to travel between the two stars. And this is typically the distance between any two stars in our galaxy. Now the question is, are there planets around other stars? Because there are so many stars in the galaxy. And this question was unresolved until the 90s. So the planets beyond the solar system are called extrasolar planets or exoplanets. And because this is India Science Festival, let us start with India. That the first claim of exoplanet detection came from India in 1855, when William Stephen Jacob at Madras Observatory, he saw a binary system. So binary system are two stars close to each other, and their orbit was very unusual, and he thought this is because of the presence of a planet. It would disrupt the gravitational potential, and so he claimed that there is a planet there, and it got a lot of attention at that time. But later on we came to know that there were uncertainties, there were shortcomings with these observations, and that's why this detection was a false positive. It was discarded. Much later in the 90s, in 1992, there were two planets. So this is the first ever detection of two planets beyond the solar system around a pulsar. And the pulsar is basically the leftover. So when the heavy stars die off, a compact star which emits high energetic radiation pulses, around that kind of a star, these two planets were orbiting. So that was in 92. And then in 95, it was the first ever detection of an exoplanet around a sun-like star, so a G-type star. And as you all know, in 2019, these two gentlemen on the right got the Nobel Prize in Physics for the discovery of an exoplanet orbiting a solar type star. And since then, since 1995, this field has exploded. So how do we actually detect exoplanets? So let me give you an example of an eclipse, a solar eclipse. So imagine you're seeing a solar eclipse. Um, this is an imagination, so you don't have to wear eye protection. When the moon slowly starts covering the sun, the brightness around us goes down. And if it is a full eclipse, the brightness then comes all the way down. And as the moon again starts moving away, the brightness goes up full back to normal. Same thing happens with when you're observing a star with a telescope. If there is a planet in front of it, it will cast a shadow, so to speak, and the intensity of light that we receive will go down. And as you can see, as a function of time, the brightness that we see from that star is going to go down. So even though we don't directly observe the planet, based on this, you can figure out that there is a planet around it. You can find the period and many other properties of this star planet system based on this. This is called the transit method. Now, there are several other methods of exoplanet detection, which I will not go into right now. So there are ground-based observatories dedicated to detecting exoplanets. Two main ones which have detected hundreds of exoplanets, so Super WASP and HARPS. So WASP is wide angle search for planets. It's an international collaboration performing an ultra wide angle search for exoplanets using this transit method. The other one is based in Chile in ESO's 3.6 meter telescope. It is called HARPS, and both of them, as I said, have detected hundreds of exoplanets. But these are not the main contributors to the field of exoplanets. It is actually the space missions, and two in particular, NASA's Kepler and TESS. So Kepler mission, even though it has been decommissioned, it is a recent mission, and in less than 10 years, it was able to detect more than 2,600 exoplanets. So highly successful mission. TESS, which is Transiting Exoplanet Survey Satellite, it has detected 2,400 exoplanets in less than 3 years. 91 have been confirmed so far, and this number is growing. So soon we'll have hundreds of thousands of exoplanets. So far, we have about 4,000 planets. So since the 90s, as I said, the field has exploded. So this is absolutely mind-blowing. So these planets are basically in three categories. The first two are what we see in our solar system, terrestrial and gas giants, as I said earlier. But there is a third category which is not seen in the solar system, but it's widely seen in exoplanets. And these are planets in between the two. These are called super Earths or sub-Neptune. So they have a mass in between terrestrial planets and gas giants. So this was something new that people saw when researching exoplanets that you don't see in the solar system. This is one example. You have, this is the Kepler 90 system. It has 8 planets, so just like our solar system, it has 8 planets. It is 2,840 light years away. And in the bottom, you can see that our solar system is there, just so that you have an idea of the scale of these planets, although the distances are not to scale. These planets, if you see that the Kepler 90, which is the furthest planet, this giant, which is bigger even than Jupiter, it is at 1 AU. 1 AU is the distance between the sun and Earth, which means that this entire solar system can be compressed within the Earth's orbit. So it is so small. And it is small because it is, I'll get into more details on why it is so small and so forth. But now we can see such systems. So now the question is, We have seen exoplanets. We have seen exoplanets, like our solar system. But are there any habitable exoplanets? So, what is habitable? Just dictionary definition is suitable or good enough to live in. And the definition of planetary habitability is the ability of a planet to harbor life. And I put an asterisk there because life as we know it. So because there is only one planet that we know contains life. And so we make estimates based on our kind of life. There is a possibility that there could be some other kind of life, silicon based life or something else, but we don't know how it would function, so we cannot make estimates based on that. So this is what we have to keep in mind, that we have to talk about life as we know it. Now this is the main concept that you have to learn today, which is the concept of planetary habitability. On the vertical axis, you see different types of stars, dim, smaller stars in the lower part going up to massive, bright stars. On the horizontal axis, you have the distance from the star. So the basic idea is, suppose you have a planet with water on its surface. If the planet is too close to the star, then it is going to be extremely hot and everything is going to evaporate. If the planet is far away from the star, then it is going to be completely frozen. So there is a zone, an optimum zone, where the planet would be able to sustain liquid water, and that is called the habitable zone around that star. And as you can see that for brighter stars, that habitable zone have to be away because of the heat. For dimmer star, that habitable zone is very, very close. And since most stars in our galaxy, they are dim, very small stars, so the habitable zones are very, very close to those stars. And I will talk about it later on. And as you can see, because we have made this definition of habitable zone based on the Earth lies right in the middle of this habitable zone, and Venus and Mars are slightly outside the habitable zone. Now there are a number of potentially habitable planets, potentially because we don't know for sure that there is life on it. There are about 60 so far. One is Mars size, 23 are Earth size, 36 are in the third category, which is super Earth or mini Neptune. Here you can see on the right, just for scale, you have Earth, Mars, Neptune, and Jupiter. On the left, you have different planets ranked by distance from the Earth in light years. So Proxima B is just 4.2 light years away from us, going all the way to Kepler 442b, which is 1194 light years. So we understand a lot about these planets, but we want to understand more. And this is very exciting. Like 20 years ago, nobody could have imagined that we would have this kind of information available to us. This is the TRAPPIST-1 system, very exciting system. Now it is 40 light years away, so not very far within on galactic scales. It's very, very close to us. It has 7 planets, and out of them, 4 of these planets are within the habitable zone. So if you see this TRAPPIST-1 system, it's again a very small star. You have all these planets. And if you see below, for scale, the solar system is shown. Both are shown together as if they are of the same size, but this TRAPPIST-1 system is enlarged by 25 times so that you can compare it. If you see below in the inner solar system, you see this tiny blue whitish color ellipse. This is where this entire system can be fit in. So within the orbit of Mercury, so close to the host star, this entire TRAPPIST system is located. And as you can see, 4 of these planets lie within the habitable zone. For comparison, if you see on the top, the Jupiter system is shown, that even the Jupiter system, its moons, Io, Europa, Ganymede, and Callisto, they have a much larger orbit. Proxima b is another potentially habitable planet. It is only 4.2 light years away. Um, you see on the left, it shows the sun, the size of the sun. On the right, that dot, that is the size of Proxima Centauri star. On the left, you have Mercury's orbit. On the right, you have the orbit of Proxima b, and this green is the habitable zone. Uh, because it is so close to the host star, it has a period of about 11 days. The mass of the planet is very similar to the Earth, 1.27 Earth masses. And we'll learn more about it. All right. So now the question is, we detected exoplanets, we have detected habitable exoplanets, potentially habitable exoplanets. Now there are any other factors that impact planetary habitability. So let me illustrate with an example. So let us say you want to travel after COVID, obviously you want to travel. I show you the weather of this place. It looks like pretty good. 16 degrees, so a little bit cold, but very moderate temperature. And you would say, yeah, definitely I would like to go to this place. But what if I were to tell you that this place is Fukushima, Japan? So the weather is great, but the radiation level is extremely high. So the point I'm trying to make is that in addition to being a planet with liquid water on its surface and so on, having a good moderate climate, we also have to take into account the high energy astrophysical environment. So what kind of radiation it is exposed to. And the source of the biggest source of radiation, of course, is the stars. In this case, you see the sun. This is an eruption from the sun. And you can see for scale, the size of our planet. So this is the scale of these eruptions. So these type of eruptions that occur in the sun, they are generally categorized or defined as space weather. And it consists of a number of things: solar winds, energetic particles emanating from the sun; flares are high energy ultraviolet radiation; CMEs are hot plasma ejected from the sun; and then you have SPEs, which are energetic protons ejected from the sun. Now, overall, this space weather is a very complex thing. Sun is highly active. So it involves many types of activities happening on the sun, how that radiation travels through interplanetary space, how it interacts with the Earth's magnetic field, how it interacts with the Earth's atmosphere, and so on. And so I will not go into too much into details, but let me just give you one example. Now, our sun, although it is active, we are protected by a magnetic field which shields us. We are protected by an ozone layer which shields from ultraviolet radiation. Plus, our atmosphere is significantly thick, which is also a shield. So that is why on a day-to-day level, we never talk about solar variability, right? But there are events that happen on the time scale of once in a century, which can disrupt our civilization. So in 1859, this event, very well known Carrington event, the latest technology at that time was telegraph machines, and there was so much charge dumped in the atmosphere that paper connected to telegraph wires caught fire. There were auroras or northern lights observed in places near the equator. And there were reports of people out in the streets at 1 o'clock at night being able to read the newspapers and books, things like that. So it was so powerful. Now, if it were to occur now, it is going to disrupt a lot of things such as aviation, satellites, power grids. There was an event recently, not so recent, a few years ago, where Canada's power grid was disrupted because of a solar event. But there is still a risk of a major event. And just before leaving office, President Obama signed an executive order to prepare the US from if such an event were to occur. And the idea is that it is going to cause major worldwide disruptions, social and economic impacts. And just in the US, the damage could be up to $2.6 trillion. And I think other countries, including India, should also work in this direction. We are in the middle of a global crisis, and we don't want another crisis to disrupt our lives. Moving on, let me once again give you an example of Proxima b. So I told you about Proxima b, how it is so close to the host star. Its orbit is at 0.5 AU, which means just 5% of the distance between Sun and Earth. It is very, very close, which means that it receives radiation 400 times higher than what we receive on Earth. So imagine a Carrington type event occurring, let us say, once a century, 400 times stronger, occurring on Proxima b. Like, what is going to happen? And so there are a number of effects, number of planetary effects of space weather. First of all, this energetic radiation changes the chemistry of that planet. So the radiation is so high. So for example, on Earth, it can break nitrogen and oxygen bonds, it can deplete ozone layer and so on. This can also happen on other planets. This radiation is so powerful that it can gradually erode the atmosphere. So over a period of time, you'll see the atmospheric thickness going lower and lower. And you have radiation dose on the surface is going to be extremely high. So even if you have life forms on the surface, they are going to experience things such as cancer and so on. And so on the right, you see such processes, all these processes on Mars. It's a very complex thing. I won't go into, but just to give you an idea that it's a very complex thing. And we use Mars to study these things and then apply on extrasolar planets. So overall, habitability is not just having right distance from the star, but you also have to consider these things such as the astrophysical radiation environment, because it governs the properties of the key properties of the planet, such as atmospheric thickness and so on, and it impacts life on the planet. And so this is where my research focus is mostly. Now from exoplanets, let me move to solar system planets. And as I told you, that one of the biggest questions is, how did Mars lose a majority of its atmosphere? Now it is very well established that Mars had liquid water on its surface a few billion years ago, which means it was potentially habitable. So we had not one, but two habitable planets potentially a few billion years ago in the solar system. Now the question is, how did it become such a dry and dead place now? At least there is no life on the surface detected so far. And so we have to understand these processes in great detail. And a number of missions, in particular NASA's MAVEN mission, has measured these things in great detail. How did Mars, because of space weather interactions, lose its atmosphere? So let me show you a quick film, a 1-minute film on how this thing occurs. So as you saw, this MAVEN mission is currently orbiting Mars. It can measure both incident radiation coming from the sun plus the response of the Martian atmosphere, and it has been a great tool. And as you can see, there have been so many missions, including India's Mangalyaan, plus 3 missions en route to the planet, which are going to answer this question in greater detail. Now, next year, there is a very exciting mission called the ExoMars mission by European Space Agency and Roscosmos. And this will be the first time where they will be able to drill 2 meters deep below the surface of Mars and look for signs of life, whether there is life, where there was life in the past, and so on. So this is very exciting. It has never been done before. And that will give us a complete picture of the habitability of Mars. Now, I'm pretty sure every one of you would have heard about the phosphine detection on Venus. So phosphine gas was recently detected on Venus. It's a biosignature gas, which means that we know that biology produces it. Now, there were 2 groups after this who came up and said that they did the analysis on their own and they did not detect any signature of phosphine on Venus. The original group then again gave more proof, more data on how they have detected Venus. And so this is still controversial, but it's still a very interesting idea, which is worth exploring. There are 2 main unanswered questions, which are, first of all, we don't exactly understand how biology produces phosphine. We know it produces, but the exact mechanism is not known. The other one is that even though Venus is so close, it is so hot and dense, and there haven't been that many missions, that the atmospheric chemistry of Venus is not well understood. So we don't know whether this phosphine is produced naturally through some geological or some other process, or is biology responsible for it. And with more observations, with future missions, we'll learn more whether this is just a regular atmospheric phenomenon or something more interesting. Then Jupiter's moon Europa. This is very interesting. It's an icy moon. It has a crust of ice. Below that crust, you have a layer. It is believed that it has a layer of liquid water. So you have ocean. And because of Jupiter's gravity, it has tidal interactions. Because of that, it has heat produced. And this heat is hydrothermal heat. And the idea is that because of this hydrothermal energy, like we have seen on Earth, life could be supported on it. So this is just an overview of what we know about habitability on exoplanets within our solar system. Just to give you an overview, I can go on and on, but we don't have enough time. So to summarize, what makes a planet habitable? So if you haven't listened to me at all, you just woken up, this is what you need to understand, that our safest bet is that, hey, if you find a planet anywhere else with ocean on it, then definitely it is very exciting, and that is potentially a habitable planet. Progress has been made to better understand the properties of these planetary systems, star-planet interactions, biology in its extreme conditions, if there is any microbial life in the solar system, how to detect it, and so on. We are learning from solar system planets a lot. We are learning from exoplanets, and we are combining the 2 things. That is my focus of research. We are yet to find microbial life in the solar system. It could exist. And what is missing is detection of life beyond Earth. So even if we have one data point, that is going to solve a lot of these mysteries. So with that, thanks a lot. If you have any questions, you can email me, you can follow me on Twitter, and so on. So thank you so much. And I'd be happy to answer any questions.
Thank you so much, Dr. Atri. That was really wonderful. And I think one great thing about your lecture was that it covered a very good variety of topics. and the very quick summary that you brought to the table at the very end was definitely encapsulated everything very well. So thank you for doing this for us. So now we've received a bunch of questions, and I'm going to start asking you right away. Let me begin with the first question. It says, in the TRAPPIST system, are the planets in the habitable zone tidally locked?
Yeah, so tidal locking is when the planets are very, very close to the stars. So, for example, let me just give you an example of Earth
Yeah,
and Moon. So, Moon is so close to us, it is tidally locked, which means
yeah.
that it all one side is always facing us. So, from our point of view, we just see our side, and TRAPPIST one system planets, because they are so close, they are tidally locked.
Okay, great. So let's move on to the next question. Um, So we've been asked if there are any books for students in schools and colleges that you would like to recommend that have personally inspired you in in astrophysics, astronomy in general. If you have a few names that you could just think of offhand, we'll put them in the chat box, and maybe everybody can refer to them.
Okay, I actually grew up reading a lot of books by Jayant Narlikar, and yeah, that was because in my childhood, other books were not available, and so Narlikar was the one to go with. Now there are a lot of books available to us. We people can order online, and I think I'll put some links in the chat box so that students can
That
refer to
sounds
them.
great.
And
Yeah,
there are tons of
that'd be great.
resources available online now. So even though they are not proper books, but professors post their lectures online and things like that. So they are extremely useful for students, things like that.
Okay, sounds great. We look forward to the links in the chat box. So we have received one question that says, how does the Goldilocks zone affect the habitability of planets?
Okay, so this Goldilocks zone is this optimum zone, and this is called the habitable zone. And so a planet within this Goldilocks zone or habitable zone is potentially able to sustain liquid water on its surface, if indeed it has liquid water. If it does, suppose it doesn't even have an atmosphere, then obviously it cannot sustain liquid water. So it needs to have certain planetary properties along with it being in this zone to have a liquid water on its surface.
Okay, sounds good. Sarita asks, if there is a chance of habitability, how would humans migrate to other planets?
Okay, so yeah, transporting human beings to another planet is extremely difficult.
Yes.
Now imagine, let us say you are doing a road trip, let us say for a weekend, how much things you pack. Imagine you're doing a road trip for 1 month or 1 year, how many things you need to carry. And so people, when they have to go to another planet, they have to not only carry with them food, water, things like that, but medicines, plus all the other tools required to maintain habitable conditions, maintain their health, and so on. So it is logistically a nightmare. We have seen in case of the International Space Station, which is only 400 kilometers away from us. Like, it is in space, but it is only 400 kilometers away from us. And over several decades, we have seen that it has been built from, piece by piece. And there are plans for people going back to the moon. NASA has this Artemis program. A number of countries have signed for it, and so that will tell us more about how to establish a base on another planetary object. The next destination is Mars, which is extremely difficult because a round trip to Mars is of the order of 3 years, and so it's extremely challenging. So right now moving humanity to another planet is sort of science fiction at this moment. And hopefully, yeah, future generations can yeah, experience more practical things.
No, definitely, very insightful. Okay, so the next question that we have is you already mentioned a little bit of this in your lecture, but the question is since Proxima b is only a few light years away, uh, significant research has been done over it for the past few decades, and what are the findings that have been done, if you could please summarize with respect to the Proxima b? um,
Yeah, so Proxima b, the star itself, is very well studied. The planet was detected only a few years ago, and
yeah.
so there is not a lot of history about the planet available. Now, the thing is, this planet is so small, as I mentioned, that it is only 1.27 times the mass of the Earth. It is extremely difficult to observe it. There have been some observations made available to us. We know about activity of the star, so there have been flares detected on this star. And so we have, I would say, very limited knowledge about this system so far, given its proximity. But people are now gearing towards dedicated observations, dedicated missions, so that they can study Proxima b system in greater detail.
The next question would be what do you think about the habitability of Titan? There are liquid lakes and it has some sort of an atmosphere. So, what's your opinion on that?
Yeah, so I actually wanted to include Titan, but then just for the sake of time, I had to remove it. But yes, Titan is definitely also one of the prime places where life could exist. It has lakes, it has organic substances, so definitely it is a place where microbial life could survive or thrive. And there are missions currently in planning where people are thinking of going there and looking for signs of life. And so, yeah, definitely very exciting place.
Here's hoping that research tells us more about Titan and habitability in the coming few years.
Yeah.
So, do you think that the possibility of the possibility of life on an exoplanet, will life have different genetic makeup in terms of life on other exoplanets? Will the genetic makeup be different?
We don't know anything about it. So now there are two possibilities. One possibility is just based on common sense that we see this building blocks of life, these amino acids, all these organic substances in space, even in comets, meteorites, and so on. And from that, our life has evolved. And so, one argument is that if there is life elsewhere, it is most likely going to be something similar. Another argument is that it could be completely different, and it could be something silicon based on the physical conditions on that planet. Um, Maybe this type of chemistry that we see is not suitable at all. Maybe some other type of chemistry is suitable, and there is no way actually to tell without actually detecting a life. And there are models, people have done calculations, people have done simulations with silicon based life and so on, but without a detection there is no way to tell.
Right. Very succinct and to the point, Dr. Atri. That was definitely insightful. Okay, the next question is again got to do with Proxima Centauri. It says recently astronomers received a radio wave emission that seems to have come from the nearby star. What is the method to confirm that wave emission?
Okay, so yeah, so generally, so this program called SETI, Search for Extraterrestrial
Yeah,
Intelligence. So I deliberately did not include intelligent life in my seminar because it is another
yeah.
topic. So this SETI program has been going on for decades now, and the idea is that if there is an intelligent life form capable of, establishing technology, capable of developing radio technology, then we should be able to detect the signature. While most, like any kind of natural radio signature, is broadband, which means it is spread over a number of frequencies.
Yeah.
Artificial signals are focused to single frequency. For example, in radio, you have to tune it to a particular frequency to listen to the radio station. And so this program, using radio telescopes, has been searching for such signals. And every once in a while, people detect unusual signals, and it is, I think, immature to jump to the conclusion that
Yeah.
it is coming from an extraterrestrial
Oh,
civilization. Most likely it is because of some terrestrial contamination. For
okay.
example, there are numerous cases where, even recent case where even the microwave that is used in offices to heat food, that generates radio signals, and that was detected, and people thought that it is coming from elsewhere. And so one has to carefully go through all the throughout, I mean, a thorough investigation of all the possible sources. And once everything is ruled out, then if the signal still persists, then definitely it is an extraterrestrial signal. And that would be indeed very exciting, although I would say the probability of it happening is extremely low.
All
I mean,
right.
it could happen, but yeah.
Yeah. No, but as you have rightly brought out, there is a lot more research that needs to be done before we can actually start giving concrete statements into for all the non-specialist audience members that are sitting here. Only research can tell us concrete statements and it's just a matter of a few years till we find something. Uh, to talk about in the whole space of extraterrestrial intelligence. And I would like to ask you one last question, sir, and this has to do with I do believe that you are involved in a lot of public engagement events as part of your work with the Blue Marble Space Institute of Science. So my question to you would be, how important do you think events like India Science Festival or other public engagement platforms are to, communicate credible science to the masses? What is your take on this?
Oh, extremely important. I think because we live in a science age, like you get up in the morning, you see your cell phone, right? Just see how much science and technology goes into that. I mean, somebody can write a book into, how technologically dependent society we live in. And this is driven by fundamental research going on for centuries. And we should all be educated about this. We should all be aware of it, so that even in day-to-day life, if you are not a scientist, if you are in some other profession, you take scientifically informed decisions, especially if you are a politician and if you control these things, then definitely science education plays a major role. I mentioned Jern Larndekar earlier. I knew about his work because he was writing, all these popular books, so that as a child I could understand such a complex subject such as astrophysics. So this is extremely important, and I encourage all scientists to do it. I encourage everyone, all children, students, everyone to be informed. This is not only exciting just for the sake of science, but for personal growth and overall outlook towards life.